It's a pleasure to open this final day of QIP. It's been a wonderful week, so thanks a lot to the organizers for that. And yeah, I have the opportunity to talk to you all about Multidimensional Quantum Walks, which is a joint work with Stacey, Jeffery. It's been a very interesting week with many interesting talks, and I can understand if some of you are a bit tired. So if you only have the attention span for one more slide, let it be this one. So yeah, we create the fastest algorithms with minimal effort. This is, of course, a very highly non-nuanced statement, and we will make it more nuanced very shortly. And to already give you a small summary, we take an existing recipe that allows you to start with a classical random walk and then compile it into your quantum algorithm. We make this recipe more complicated, but I would say also a little bit more tasty. And then we apply this to two applications. The first one being the welded trees problem, and the second one being the k-Distinctness problem, where you're looking for k-collisions. Once we get to these applications, I will explain them and I will show you why you should care about them. But first, we will start with the main ingredient of a recipe, namely random walks. So a classical random walk is a great tool when designing algorithms because the algorithm becomes very intuitive and it mimics someone walking on a graph. So we have to start somewhere on this graph. And to do this, we sample a vertex from the stationary distribution of the random walk. If this doesn't ring a bell, you can just think for the sake of the argument of uniformly random picking a vertex from the vertex set. Now, the goal of the walker is to end up in a marked subset of the vertices, and ending up in such a vertex will correspond to finding a solution of the problem that you're trying to solve. So at each point, the walker verifies, am I already in a marked subset? And if not, I will sample a neighbor of my current vertex and then transition towards this neighbor. Again, the sampling is done according to some probability distribution that characterizes the random walk. So if we want to analyze the complexity of such an algorithm, we need a couple of ingredients. So if we know the cost of setting up the walk, so sampling the initial vertex, if we know the cost of verifying whether we are now currently in a marked vertex, and if we know the cost of sampling a neighbor and then transitioning towards this neighbor, then we almost have all of the ingredients to analyze the complexity of this algorithm. The only thing that's left is to kind of find out how long we'll be stuck in this while loop. So this is given by the hitting time of the random walk, and it is the expected number of steps that the walker will have to take, starting from the stationary distribution, to end up in one of these marked vertices. If you have all these ingredients, then it's now kind of straightforward to see that the complexity of this algorithm is as follows. This seems like a great framework if you're dealing with graph problems, but in fact, you can abstract many other problems to kind of fit this language. So to do that, we show a trivial example, namely the search problem. So this is not inherently a graph problem, but it fits this model very nicely. So we consider a n-bit string x. All the values are set to 0, except for one index where the value is 1. And your goal is to find this 1. Now, to this, we can assign the n-complete graph, where all the vertices of the graph corresponds to indices of this string. And it's complete because you have the freedom to just query any index in this list, and it doesn't depend on which index you queried previously. There's no kind of nearest neighbor interaction going on. And there will be one marked vertex which corresponds to the one index that you have to find, namely the one where the 1 is stored. So sampling a vertex will just mean that you're sampling a index. And if we care about query complexity, then just choosing an index is free. So this will be 0. Now, to verify whether a current vertex is marked, we have to query this index and verify whether it's a 1. So this will have query cost 1 to it. Now, finally, sampling a neighbor just means sampling a new index. And again, we're caring about query complexity, so this will just be 0. And if you analyze the hitting time of an n-complete graph, which is the single marked vertex, then you can upper bound this by n. And if you plug in all these values, you find that this classical random walk will run in a complexity n. I'm like omitting big O notation. And of course, this is not a very interesting algorithm, but it kind of shows that you can abstract many problems to fit this graph setting. Now, okay, this is all classical. What if we want to move to the quantum setting? Can we kind of keep this intuition? And luckily for us, we can. So Szegedi came up with a wonderful machine that allows you to start with a classical random walk. You can run it through this machine, through this compiler, and you end up with a quantum algorithm. And this quantum algorithm can have up to a quadratic speedup compared to the classical random walk that you started with. And this is great because it allows you to create a quantum algorithm without knowing kind of what the machine does. You don't need to know anything about quantum algorithms. The difficulty lies in designing the random walk, which are mostly discrete math arguments, combinatorial arguments, and we have a lot more experience in those fields than in the shorter frame of quantum algorithms. So again, you can just use this machine without understanding it and just use the results, kind of the fact that MIP star is RE. Now, over time, this machine has been made more complicated. It has also been made more sustainable by Beloffs, and this is also referred to as the electric network framework. And I will not delve into the specifics why this machine is more powerful, but this was kind of the most powerful framework to discuss quantum random walks in, and this was our starting point. So we took this machine by Beloffs, and we made it more complicated. But as a result, if you now start with the classical random walk, we exhibit an example where the resulting quantum algorithm can actually achieve up to exponential speedup. Now, if you're thinking about random walks and you see exponential speedup, then many of you might start thinking about welded trees. Now, in the welded trees problem, we consider two binary trees with roots s and t, and the depth of each of these trees is n. We will now weld these trees together in the middle, and we obtain a graph where every vertex has degree 3, except for our two roots s and t. Now to each vertex, we assign a 2n bit string, and at the beginning, we only know the bit string associated to s. Our goal will be to find the bit string associated to t. And we can learn from this graph. We can do this by querying any vertex, and we'll obtain a list of its neighbors. So what's important is that even though you learn the neighbors, you do not know kind of the orientation of the neighbors. You don't know which neighbor is moving us towards t, this is where we want to go, and which neighbors are moving us back to s. So because at the beginning we only know the bit string of s, this problem is kind of set up in such a way that if you were to try to tackle this problem, there's not much more that you can do than starting s, the only place that you know, and then just query neighbors and start random walking. And at the beginning, we have more neighbors moving us towards the middle, so this goes very nice. But once we're in the middle, we kind of get stuck there, because we do not know which neighbor is moving us out of this middle. And this is kind of the intuition why it's classically hard. And if I'm saying it's hard, I mean it's very hard. So in the original paper by Childs et al., they showed that this problem does take an exponential number of queries, exponential in the depth of these trees. And for us, as you know, designing quantum algorithms, this is bad news, because if we were to put it through Beloffs' machine, or we start with a random walk which takes an exponential number of queries, and we end up with the quantum algorithm that still takes an exponential number of queries, because these machines were only able to achieve up to quadratic speedup. But the reason why we care about welded trees is that it was shown that quantumly you can in fact just solve this problem in a polynomial number of queries. And this is why this problem is so interesting. So it's a little bit contrived, but we always care about super polynomial speedups. So if you were to put this, so the walks that have been given to solve this problem in a polynomial number of queries, they're in fact quantum continuous random walks, and these differ from kind of the walks that are obtained by the Szegedy or Beloffs machine. I will not delve into the specific why they're different, but the main problem is that we don't really have a machine yet to generalize these walks and to kind of extend this breakthrough result and see if we can achieve these kind of speedups elsewhere and use their techniques elsewhere. So in our work, we show that if you were to put this welded trees random walk through our machine, you can in fact obtain a quantum algorithm that just traverses this graph linearly. And so you find t in just a linear number of queries. So even though we already knew there was an exponential speedup, we can now sort of see that maybe there's a machine that can generalize these effects. So how does our machine work? How does it kind of achieve this? So like I said, we extend upon the machine by Beloffs, and we do this in two main ways. One with something that we call alternative neighborhoods, and the other technique by something that we call edge composition. And I will now kind of give a high overview description of both of these techniques. So to start with alternative neighborhoods, let's go back to the welded trees graph and consider a vertex in the right-hand side. Then it has three neighbors, and we can label them by the children, C1 and C2, which are moving us toward the middle of the graph, and the neighbor P, the parent, that will move us towards T. This is where we want to end up. Now, if you kind of go into the inner workings of these Beloffs or Szegedi machines, then the resulting quantum algorithm must be able to reflect around a weighted superposition of the neighbors of each vertex. Now, this may seem a bit technical, but intuitively, if you were to measure this state, then you're actually just sampling a neighbor. So this is kind of the intuition that you can keep. So with this intuition in mind, we want our algorithm to move towards T and hence towards the parent. So it makes sense to put a little bit more weight on the parent neighbor than on the children. So we would love to be able to reflect around the following state. So we put a little bit more weight on the parent than on the children. These minus signs, they occur due to technical reasons, and just intuitively think, P is the right direction where we want to move, the children are the wrong direction, so we obtain a minus sign there. Now, if these machines were able to reflect around this state, then we could, in fact, obtain more than exponential speedups. But like I said, they can't. And the reason is because of the oracle model that we had for this welded trees problem. So we do not know which neighbor is the parent and which neighbors are the children. So it's, in fact, too hard to kind of construct the state and then reflect around it. So sadly, we are unable to do this. But our alternative neighborhood techniques kind of resolve this issue, and they resolve it in the following way. So in our machine, we do not know which vertex is the parent, so we consider 3 alternative neighborhoods of our vertex. One alternative neighborhood where we consider V1 to be the parent. And here V2, V3, V1, V2, V3 are just the 3 neighbors that we obtained from currying. So there's also another alternative neighborhood where we consider V2 to be the parent. And then there's a final alternative neighborhood where we consider V3 to be the parent. Now, we do not know which of these neighborhoods is the correct one, but we do know that the correct neighborhood is one of these 3. So instead of just reflecting around the span of the correct option, we reflect around the span of all of these options. And we're, instead of reflecting around just a state, we are now reflecting around a multidimensional space. And this is why we call our walks multidimensional quantum walks. Now, contrary to QAP, you don't get free lunch here. So this is not always possible, and it requires a careful analysis. And luckily for us, this works for the welded trees problem. This works for the k-Distinctness problem. But we do make the machine a little bit more harder to use. Well, now the other kind of technique in which we extend the Beloffs framework is edge composition. And in fact, this is a special case of quantum subroutine composition, which Stacey talked about on Monday. If you were there, great. If you're affiliated with the quantum wormhole experiment, this is a great time to go back in time and see the talk. And otherwise, I will make sure to give a small summary. So in the welded trees graph, we have a very nice symmetrical graph, and transitioning from any vertex to its neighbor is just as hard independent of its neighbor. So we have, say, update cost U1 attributed to every edge transition. But perhaps some of you are familiar with random walks, and you know that sometimes you want to walk on a Johnson graph. Perhaps you want to walk on a Johnson graph of like collisions that you're storing. And hence, to make some edge transitions, you might need to run another quantum subroutine like Grover to actually move from one vertex to the other. So you might want to insert another quantum algorithm in your edge transition. And as a result, this edge transition becomes a lot more expensive. So instead of U1, we now have U2. And classically, this is not a huge problem. And if you're analyzing the update cost of your random walk, then you can just average over the update costs. So perhaps you have one edge that's way more costly, but it occurs with a very low probability, and this is okay. But in a quantum walk, we want to be able to, walk these edges in superposition. And then if you take an update cost that's kind of lower than one of these branches of the superposition, then after one step, you might not have completed all of the branches, and this doesn't really make a lot of sense. So sadly, in kind of the older random walk frameworks, you're usually stuck with taking the maximum update step, and this can be very costly in some instances. So the idea of edge composition is kind of simple almost, because you just split the costly edge into multiple smaller edges, each of which that have kind of the same update cost as all your other edge transitions. And this really allows you to cut the update cost down. It does occur in a graph with a bit more edges, but if you go through the analysis, this is always strictly better. This is never more costly. So, as I said, we put the welded trees problem through our machine, but we also put the k-Distinctness problem through our machine. And a warning, we will now be caring about time complexity. So far for the welded trees, we've just been doing queries. Now we'll also be counting time complexity. So what is the problem of k-Distinctness? Consider a list of n elements, and all these elements are like polynomial in size. Just think of a number. And you might be more familiar with the element distinctness problem. So here you have to decide whether this list contains a collision. So a collision is just two distinct indices whose respective values in the list collide. Now, the k-distinctness problem is a generalization. So instead of looking for a collision, you're now looking for a k-collision, and this makes the problem harder. Classically, this problem is not very interesting, but quantum it is. And kind of understanding k-distinctness, trying to improve its upper and or lower bounds has really improved the techniques that we use for either lower bounds or upper bounds. So originally, a random walk was exhibited by Ambines that solves k-distinctness in a sublinear number of queries. And its time complexity kind of matched up to polylogarithmic factors, because this is a nice thing about random walks. If you analyze their time complexity, it's kind of straightforward to do. And later, a query upper bound was given by Bellows, but this was given as a dual to the adversary bound. So we know that this was an upper bound on the query complexity, but we didn't really have a concrete algorithm whose time complexity we could analyze. But if you look at the problem of k-distinctness, I mean, you're going to query elements and you might compare them, but there shouldn't be much more that one could be doing. So it makes sense that the time complexity should actually match the query complexity, perhaps up to polylogarithmic factors. But this has been an open problem for more than 10 years. It turned out to be very hard to kind of show the time complexity of k-distinctness to match the query complexity. And especially when k kind of grows, this gap becomes quite large. So it's important to note here that k is always a constant. So if we kind of take the classical random walk that's already kind of there in the Bellows dual adversary solution, and we kind of push it through our machine, then we obtain a quantum algorithm whose time complexity actually matches that of the query complexity by Bellows. And hence we have kind of bridged the gap between the time complexity and query complexity. So to summarize, we create the fastest algorithms with minimal effort as long as they're kind of created from a random walk. And we've exhibited this machine that allows you to start from this random walk and then create a quantum algorithm. And we apply this machine to obtain new results for the welded trees problem, as well as for the k-distinctness problem, respectively in query and time complexity. So you can find our paper on the archive, and if you want to random walk together, you can address me here. Thank you.